I want to tell you a bit about the composition of communication protocols in general. Of course, the motivation comes from looking at quantum communication protocols, because that's my area of research. But what I'm about to tell you generally applies to any sort of protocol in the end, because no protocol exists isolated. Like whenever you're looking at, for example, a quantum algorithm or some sort of communication protocol, you will always use it in a bigger system of protocols that you're doing. So in principle, you should always think about, okay, does whatever I prove about the protocol I look at, does it hold if I embed it into a larger communication or whatever system? And I want to show you a bit that it's not always trivial that you're able to embed it into a larger network without having security issues. So I want to tell you a bit about some examples from the past, like what we have observed, where things go wrong that you didn't expect to go wrong simply because you put the protocol, like you connected a protocol to other protocols. Okay. And for that, I want to start with a bit of background on like cryptography, on quantum cryptography, because that's where the examples come from, and that's where my initial motivation comes from, because I'm studying quantum cryptography. Okay, so generally, the goal of a quantum cryptographic protocol, or the one that I want to look at, is to establish a secure channel between two parties. So in cryptography, we always call these parties Alice and Bob, and I've chosen some cats to represent them here. And they want to communicate with each other. So they want to send messages to each other in a way that no one can tamper with these messages and no one can learn the content of these messages. So that's what we mean when we say there's a secure channel between two parties. Okay, so the task is you want to somehow build this communication channel with the resources that you have. Because the two parties will be, in general, at distant locations. So they don't necessarily meet in one point. That means you need some sort of protocol that works if the parties are in distant locations and may never actually meet each other in person. We do know how to solve this problem, completely classically, actually. That is the so-called one-time pad. And this is information theoretically secure, which means you don't need any computational assumptions or anything for the security. And the way it works is quite simple. So you have Alice and Bob, and Alice wants to send a message to Bob via a public classical channel. And the way the encryption scheme works is that she has this message, which is generally just a bit string, and she also has a key. And she just needs to add the two bit strings together to get some ciphertext. And this ciphertext can then be sent over the public channel, because the way why this works is if you have a completely random key, then also the ciphertext that comes out of it will be completely random. That means it doesn't contain any information about the message. Like just if you only read the ciphertext, it has no information about the message. Only in combination with the key, you get information about the message. And that's why it can be sent over this classical channel. And then Bob will receive the ciphertext, and he's supposed to have the same key as Alice. He can then just add the two bit strings together and get the original message out in the end. Okay. This works, and this is secure if the key fulfills certain properties. Like the key, as I said before, it has to be uniformly random in order for the ciphertext to be uniformly random and therefore not containing any information. It also has to be identical for Alice and Bob, so that Bob in the end can get the same message out of it. And importantly, it has to be unknown to Eve. Eve represents the general adversary, or all possible adversaries that could try to attack the scheme and read the message. And of course, it has to be unknown to the adversaries. Otherwise, they could just do the same as Bob does and retrieve the message with the key. Okay, so one can show that this allows for unbreakable encryption, like the scheme can't be broken, has been shown by Claude Shannon in 1949. But in the end, we have just shifted the problem. So we want to build a secure channel. We now know how. But the new problem is we have to distribute this cryptographic key somehow with exactly these properties to two parties who are in distant locations. Okay, I will get back to that. Okay, but that means that, if I represent this one-time pad scheme here with this box, that means we need an additional protocol that distributes the key before that. So we need some sort of key distribution device that generates these keys and distributes them to Alice and Bob. And generally, this device, it depends on how exactly this works, but it will leak some sort of information to an adversary, and one has to specify that. Okay. But the important point in light of this talk is that we have to compose two protocols in order to make this work. So the combination of the two protocols then gives us this secure channel. And so we have this guarantee that the one-time paired encryption scheme is unbreakably secure, but only if the key that is made by this key distribution device fulfills these three properties. So we also need a guarantee that the key distribution device produces keys that fulfill these properties. And then we want to combine the two guarantees to a new guarantee. Okay. And the idea, what we would like to have, is that you can prove individual security statements for each protocol that you have in your scheme, and that will automatically guarantee the security of the combined scheme, of the secure channel. So we want to individually talk about security for the one-time paired and for the key generation scheme, and then just adding the two security statements should give us the security guarantee for this whole channel. We don't want to have to, if we have individual guarantees, we don't want to have to go again when combining them and come up with a new security proof. And implicitly, that's also what people assume when they talk about security of individual protocols, that it will hold in a general context. Okay. To understand the issues that come with this, I first want to go a bit into more detail, like why we're looking at quantum cryptography and how the security proof generally works, because this will help us to understand where these examples that I show you later come from and why these issues arise. Okay, so first I want to say something about why we are looking at quantum cryptography and we're not just happy with classical cryptography. And to visualize this, I like to draw this graph that shows the insecurity of a protocol over time. So it basically shows the probability that a certain scheme is broken and how it develops with time. And as an example for a classical algorithm, I like to take the RSA algorithm, which is widely used in today's encryption. And it is based on the assumption that factoring large integers into prime numbers is a hard task. Okay, and if you want to use it, you would, at the beginning, you have to choose the parameters of your encryption protocol, like the key length, for example. And you would choose it in a way that you believe the probability that it gets broken is very small. But if you keep the same parameters and let it run for a longer time, this probability of being broken changes. Because there are hardware evolution, so our computers get more powerful, and then simply by brute force attacks, it gets a bit more likely that they will be able to break it. And there might also be some algorithmic discoveries that make schemes more efficient that try to attack the RSA algorithm. Okay. At some point in time, there might be a universal quantum computer. We don't know when or if, but it's possible that this point in time will come. And since you're probably aware of, we know that quantum computers, they can efficiently factor large numbers. So as soon as we have a reasonable, useful quantum computer, this will make the RSA algorithm insecure. So we'll jump to this point, which is where the protocol becomes insecure, and then we'll just stay there. Okay, so that's the issue with the RSA algorithm. We know already a quantum computer would make it insecure, but even before that, these smaller evolutions force us to always update the security parameters. Okay, and so because people are aware that quantum computers might be a threat in the future, they research alternatives. And one possibility is just to go to other classical encryption algorithms where we don't know an algorithm that breaks them, be it classical or quantum. And this is called post-quantum cryptography. But you can draw a similar graph like this. So there will be some evolution like this. And at some point in the future, there might be an algorithmic discovery, be it classical or quantum, that also renders your chosen post-quantum algorithm insecure. Since we can't prove the security of these things, but it's only based on our belief that certain tasks are hard, at some point in the future, there might be a point where they become insecure. Okay. I want to put now quantum cryptography protocols in contrast to this, because if you draw the same thing for a quantum cryptographic protocol, you get just a flat line. It is not affected, the security of the quantum protocol is not affected by hardware evolution or algorithmic discoveries, and also not by the existence of a quantum computer, because from the beginning, where you show its security, you factor in an adversary who is all-powerful. It's only restricted by the laws of quantum mechanics, so whatever happens in the future, as long as it stays within the laws of quantum mechanics, we're good. The security stays the same. Of course, this is a bit simplified, and if you look at real protocols and real devices, there come additional problems. But this is the underlying fundamental idea of quantum cryptography. Okay. And how is this achieved? It is because we have a security proof that allows us to show this level of security like mathematically rigorously. And the general structure there is that you start with some assumptions, for example, that quantum mechanics is correct. That would be a very basic assumption. And you want to show a certain security guarantee, namely that the quantum protocol cannot be broken by anyone within the laws of quantum mechanics. And the security proof is then like a line of mathematical statements that connects the assumptions to the security guarantee. Yes, and then, so these three elements of the security proof, they're equally important. Like we need to know how we can actually mathematically formulate the security guarantee. We need to be clear about what we assume about the devices, the information carriers, like photons, for example, about our adversary. And then we need to figure out what the mathematical tools are that we can use to connect the three things. So there are these three pillars, and each of them is important to guarantee security in the end. So in the end, it's a mathematical theorem, but of course it should match your physical reality, because in the end you have a physical device, and that's supposed to be secure in an application. Okay. We can actually do such a security proof for RSA encryption, if you think about it. So the security guarantee that you want to show there is that messages that are encrypted with RSA, that they cannot be decrypted. And your assumption is, as I mentioned earlier, that large numbers can't be factored efficiently. And what the security proof does is it does a reduction argument. So it shows more or less that a procedure that allows you to decrypt the messages encrypted with RSA would also allow you to factor large numbers efficiently and therefore cannot exist. So the security proof in principle it's solid. Like, the issue is just that we know the assumption is not fulfilled as soon as you have access to a quantum computer. So this illustrates that we need to be really careful about what assumptions we put in there, because if you put in an assumption that is not met by the real device, then the whole statement is invalid. Okay, now I want to show you some cautionary tales where things went wrong because of composing protocols. So the goal in the end is to have a solid, rigorous security proof for the device you're looking at, but you need to factor in, this is part of this, how you choose the security guarantee in the end, you need to factor in that you will compose these protocols with other protocols in the end. And this might open up security loopholes. Okay. For that, I want to show you two cautionary tales where things have gone wrong in the past, which people didn't expect. So the first one is you need to watch your definitions. You need to choose the security definition, your goal of what you want to show carefully, so that composing protocols doesn't make it invalid. Okay. And then, so the question is how do I define security? And here I want to look at the example of a key distribution device, like quantum key distribution device, which is supposed to solve the problem of distributing a key to the two parties using quantum mechanics. So for the purpose of this presentation, it's not really important how exactly this works. We just want to look at how can I formulate the security of it in a mathematically rigorous way. And for that, we only need to be clear about what the device has to achieve. And we know that from the properties of the key that the one-time pad needs. So if you recall, when we talked about the one-time pad, then the key had to fulfill three properties: being uniformly random, being the same for Alice and Bob, and being unknown to Eve. And somehow you now have to mathematically capture what that means for the output of this QKD device. Okay, there was I have a first proposal for a security definition, and this is what has been used actually in the early days of QKD, where they tried to do security proofs. They started with this security definition. And if you look at it, it seems to capture exactly what you want. So there are two properties. The first one says the probability that the keys between Alice and Bob, they are not identical, is very small. Of course, ideally you want to have it 0, but it has turned out that is that's not possible to achieve that. But you can achieve very small probabilities, like 10 to the minus 8 or something. So you're fine with these tiny probabilities of failure. And this one would capture the second property, so that the key has to be identical for Alice and Bob. And then the second property captures the other two properties of being random and unknown to Eve. Namely, it says that, okay, at the end, the quantum device, like this QKD device, it will output the two keys, but it will also output some sort of information for the adversary, because the adversary might have somehow interacted with it. And that's fine, as long as this information that the adversary has fulfilled certain properties. And in this definition, you say, okay, in the end, to really have useful information on these classical keys that are output, the adversary needs to measure the quantum system. But we don't restrict the kind of measurements. We say she can do whatever she likes, whatever measurement is possible with quantum mechanics, and then we take the worst case of this. Okay, that's here the supremum over all possible measurements. And what we want to achieve is that the real situation described here by a probability distribution over the key and the outcome of Eve's measurement, this is supposed to be very close to an ideal situation, where the ideal situation is that this probability distribution factors, which means the adversary and the key are completely independent of each other. And the probability distribution of the key is a uniform distribution, which we need for this uniformly random property. Okay. And we say, okay, the difference between the two probability distributions has to be really small if I take the worst case over all possible measurements. Okay. So this security definition seems to capture exactly what we like from the key, and it seems safe and solid. Okay, one can show that the second property, it's equivalent to a property of the accessible information, which is the mutual information between the key that Alice gets and Eve's outcome of the measurement, where you just take the worst case again over all possible measurements, and then just compare just calculate the mutual information. It's called the accessible information for Eve. Okay. So the question is, will this provide a secure key distribution device that we can safely use in any application, or is there an issue? And there actually has been an issue, which you can see once you actually use the key in an application. So everything's perfectly fine if you only want to create a key but never use it. Then this security definition gives you a secure key, but you didn't get very far because you're not creating keys for fun. You want to encrypt messages typically. Okay, and then you can see if you use this QKD device in combination with a one-time pad, the whole thing can become insecure. And the issue is the following. So if you recall the security guarantee, we have the optimization over all possible measurements that Eve can do. And what this tells you is that, okay, you force Eve to do a measurement at this point before the one-time pad protocol runs, and then you take a worst-case evaluation of the whole situation. But now that you see it in combination of the two protocols, it seems very unnatural to put the measurement in between the two protocols. To analyze this whole secure channel, what would be much more natural is to put the measurement in the end and then make a worst-case analysis of the whole thing. And then allow Eve to keep her quantum information as long as the whole protocol runs. Because the problem is, it's a composability issue here. It's called information locking, which is a property of this accessible information. The optimal measurement at the end of the protocol might differ from the optimal measurement at this point T1, when the key distribution protocol has ended, because the adversary could have learned something during the run of the one-time pad that would help her to get a better measurement than she had here. And one can actually make an explicit attack on this scheme that shows that you can get information about the message, even though the key has fulfilled the security guarantee in the beginning. So the adversary can actually get clear text of the message, even though your security guarantee was fulfilled. Okay, and this, in the end, caused some paradigm shift in QKD, where people move from this security definition to a different one to avoid this issue. And it's not surprising that in the paper where they found this, the two latter people, Bariska and Maurer, they're classical cryptographers. Because in classical cryptography, people were aware that composition of protocols is an issue. They've seen that in classical cryptography a lot before. But people in quantum cryptography weren't as much aware because they were physicists. Okay. And then this was solved by coming up with a different security definition that was derived in a way where people took into account that you want to compose protocols. Okay. And it was like, the idea was that you take the QKD device and the outputs, as before, the keys and information for Eve, and you describe the output as a quantum state. You say, okay, how would the ideal quantum state look like? And it has this form, which captures all three properties that you want to capture. So this factor in the beginning, this is the probability for a certain key to appear. And this means that the probability is the same for each possible key that can appear. This captures the uniform randomness of the key. Then here you have key registers for Alice and Bob, and you see the entry in the register is the same for Alice and Bob. So this captures that Alice and Bob want the same key in the end. And everything here, the key systems are in tensor product with the adversary. So the adversary is completely uncorrelated with the keys, and she doesn't have any information with the key. So this is the quantum state that captures the ideal situation at the end of the QKD protocol. And what you need to show is that your real device, where you, like for example, characterize the states that appear, the measurements, or your channels, that this real device is close to the ideal device. Like this is the new security definition. We say, okay, if the distance between the two quantum states is small, then your device is secure. And here you don't force Eve to measure at any point. Everything just stays quantum. And in fact, this has been derived within a whole framework that was made for composable cryptography. So the fact that it has been derived in this framework ensures that it is really composable. And here, you can see that the issue I talked to you about before with the measurement, this certainly cannot arise here. But also no other issues regarding composability can arise here. But this shows how factoring into the composition of protocol helped to see a security flaw that can actually be exploited in practice and make it better. That brings me to my next example, where also factoring in composition of protocols has shown that certain things are insecure. And here it's about the assumptions that you have in your protocols. Before it was a definition issue. And here we talk about the assumptions that you put into your security proof and how that might cause issues once you compose protocols. In this part, it's about a part of QKD, it's called device independent. I've given you here a schematic of, this is generally the kind of setup that you have in a QKD protocol, where the two parties, Alice and Bob, have some quantum channel available, some classical channel. And in the lab, each of them has a quantum device called Q, a classical device called C, and some random number generator called R. And the important part for device-independent QKD is that these quantum devices, QA and QB, they're seen as black boxes. They're not characterized. It's not said anything about what quantum states they are, what measurements they are. It's just a black box, and you just record classical in and outputs of this. But you don't want to say anything more about this. And we do have security proofs for these kind of protocols for the composable security definition that I showed before. Taking that security definition, we can show that this protocol is secure. So you would think, okay, then I'm done. Everything's fine. I have the right security definition. I have a solid security proof. What can go wrong? Okay, what can go wrong in this case is when you start composing the protocol with itself. So you want to have many keys. In round one, you generate key one for the two parties. In the next round, you generate a whole new key, and you go on. And this is how you would generally use these protocols in practice. You don't just build a setup to generate one key. You want to have multiple keys. Okay, but now the quantum devices, we say they are black boxes. We don't make any assumptions about the inner workings. That also allows for the quantum devices to have some sort of memory. So the quantum device can memorize the key from the first round, and that can influence how the key in the second round is generated in a way such that the standalone security of each individual round is not touched. That is still fine. But overall, we can see that the value of the keys can be leaked. The problem is that the general behavior of the quantum devices can leak information about the key. So an example is, let's say in round 2, like a QKD protocol, it generally consists of many rounds because you want to have a key that has many bits. And for each bit, you need an individual round. And then the protocol in the second round could just start to abort at some point. Like it just aborts all the time after a certain amount of rounds. And because the quantum devices, like they can just do that. If they just don't react anymore, your protocol just aborts from this point on. And the key in the first round, it's a bit string, so it represents a number. So the position in the second round from which it is aborted could coincide with the number that the key represents. And in this way, the behavior of the devices just publicly reveals the value of the first key. And so the security of your key was perfectly fine if you just look at the first round isolated. But as soon as you try to make a second key, the security of your first key is just invalid. You can't use it anymore. And you see, this is an issue that, again, comes up because I compose the protocol. Now I just compose it with itself, but it should still stay secure if you have a reasonable sense of security. And the issue is that this composability framework that we used to derive the definition I showed you before, it doesn't factor in that you have devices, that your devices have memory. So it implicitly assumes that whenever you compose protocols, in each run there's a fresh device that like has no memory of what happened before. But that's of course completely unrealistic. And so this device-independent QKD is only secure if we assume that the devices forget everything in between two key generation rounds, or if you always use fresh devices in each round, which would become very expensive after a while. But this assumption goes against the fundamental idea of device-independent QKD, because the paradigm is that we don't assume anything about these devices. And that's because it's much more secure if you don't have to assume anything. That's why this whole thing was developed. So adding an assumption on these quantum devices goes against the idea of device-independent QKD. And also, another issue is that people only realized this issue a bit later because they didn't factor in the composition of these protocols with itself. Okay, so this issue has not yet been solved. That's still an open issue, even though it's been known for at least 10 years or something. It hasn't been solved because all the frameworks that we have don't allow you to factor in reusing devices. But generally, like this is a more general issue. Of course, you want to reuse your devices, so you need to be very clear about when you can do that and under which assumptions. So what we need to do is we need to extend this framework to allow for reusing devices. And this is like the last part of my talk. I want to talk about some work that is joined with Renato Renner in Zurich, which is still in preparation. We're currently trying to write up the paper. So I want to tell you a bit about how we're trying to extend the existing framework in a way that allows for reusing these devices, but it's even more general. Like the basic idea is that you add space-time to your framework, and then you have to put your devices and all your protocols in space-time and see how that composes. Okay, and for the rest of the talk, I want to tell you a bit about the main ideas of this framework, and also what kind of problems can be solved with it in addition to this device-independent QKD issue. Okay. The good thing is, like I said, it's an extension of the previous framework, but you don't need to know anything about the previous framework because it's actually like quite fundamentally different. And I think the main ideas can still be explained in a very, like I can visualize them so it's easy to understand. Okay, actually, the way we got into developing this framework was we asked a different question. We wanted to know how can we define randomness? Because randomness is an important primitive in many cryptographic protocols, but if you look at the literature on randomness, there are millions of different kinds of definitions. Some make no sense, others seem like reasonable, but no one agrees on this. In quantum key distribution, we have one definition where 95% of people agree on this is the correct one, and we have a lot of trust because it has been developed within a composability framework that takes care of everything. But in randomness, it's like chaos. And so we ask ourselves, okay, what is a reasonable definition of randomness? Okay, so first, then you need to think about, okay, what do I even mean with randomness? So if I would ask you, could any one of you give me a definition of randomness, a mathematically rigorous definition of randomness? Could you write down a formula? I think many people have an intuitive idea of what randomness is, because it does appear in our daily lives. But really writing down a mathematical formula, if anyone has an idea, I'm happy to hear that. But otherwise, I will present you my idea and show you why it was so difficult to reach this formula. So intuitively, what you want to capture with randomness is, I've now the space-time diagram, so everything is now set somewhere in space-time. And randomness, it's some sort of system within space-time. I just call it R. And what being random means is this, that no one who has access to all the information that was in the past, in this area E here, if you have access to all the information in that area, you still cannot predict the value of R. That's what it intuitively means, that this is randomness. Okay, but of course I want to capture it mathematically. And if I want to do it classically, I would have an idea how to do that. I write down the probability distribution of my system R and the rest of the world that is called E. And similar to how it was in the QKD setting, I want this probability distribution to factorize. I want the R system to be completely independent of the E system. And in addition, the probability distribution should be uniformly random. But of course, in the end, my world is quantum, so I want to generalize this to a quantum setting. And this is not a straightforward step. I can't just write the same thing with quantum states. I can't just say, okay, here's the quantum state of R and E, and it's just in a tensor product, because the state of the region E doesn't exist. You can't just generally write down a state of a region in space-time, because what could happen, for example, is that within this region you have some system, some quantum state, rho B, and in space-time it just undergoes an identity evolution, and here you have the same state rho B. And if all of this is part of your region E, if this is all E here, and then if you write down the quantum state of rho E, you would just have a copy of rho B. So this would just allow you to copy quantum states. So we can't just generally allow the state rho E. We can't just generally write it down. Okay. But we would like to have some way of formulating this that captures the idea, the essence of it. Namely that the information content between the two systems is somewhat independent of each other. Okay, so we actually started developing this framework and got inspired by quantum field theory, because it was in the semester where Renato gave a course on quantum field theory and I was the head teaching assistant. So we discussed a lot about how quantum field theory works and the basic ideas. And one part that we certainly need is the space-time, because space-time tells us which regions we're interested in, which regions we would like to talk about. And that could be any sort of region, a general region, A, B, or C, maybe some light cones that define regions, in the randomness example, or just some time slice sigma here. So the space-time tells us which objects do I actually want to talk about. And on the other hand, we added this just a general Hilbert space that we called the panorama space. And this is supposed to just capture the information content. So here things have no meaning in terms of space-time, in terms of points in space-time. This is just the information. And the state in this space, it's supposed to just contain all information about the world at all times. And because here, the space-time points have no meanings, it's just a quantum state that tells you this is all the information I have about the world. It's also supposed to capture limitation of information. If you want to, in space-time, measure a system, measure its position and momentum at the same time, then your state on the other side is supposed to tell you, well, you can't do both of them at the same time to an arbitrary degree of precision. And we got this idea for this part from the objects in quantum field theory, because where you have the field, and you can ask it questions about what's happening at this position. and it will tell you things about like everything, all the positions in space-time with no restriction, and you can talk about correlations and everything. And so we wanted to have a similar object for our setting that you can ask it questions. Okay. So the most important part of this is the connection between the two, obviously. Like the left-hand side tells you the regions you're interested in, and the right-hand side tells you the information content. And now you need to connect the two. So you can ask the panorama state, okay, what's the state of region A, for example? And then you need a map that extracts exactly the information you need about a certain region. So the important part of this framework is coming up with these maps that extract information from the Hilbert space to these regions in a way that represents how like information exists and flows and everything. An important aspect for this is that generally you don't need all parts of the whole space to talk about a tiny region in space-time, but there will be an area that contains all the information about this part of space-time, and we call this a representation of the space-time region. Importantly, they can overlap, which makes things really difficult, because this is a situation that is unfamiliar to us. Where in normal language of quantum information theory, if you translate situations of standard quantum information theory to the framework, you don't encounter these overlapping representations, as we have seen. But if you have general regions, then sometimes this happens, and it makes things mathematically very intriguing. Yes, but generally we allow for this. And this representation, it's just defined as something, if you extract information from the whole Hilbert space, then you don't need the whole space, but you can trace out everything except the representation and then map. So it's independent of the rest of the Hilbert space. Okay, to give you a little example, if you want to model just a unitary map in the space-time of two quantum systems here and two quantum systems here, then the input systems AB will have some sort of representation in the panorama space, and the output systems will have the exact same representation, because the representation captures the information content, and the unitary preserves this information content. No information gets added or gets lost, so it's just the very same representation. You just need to then create these extraction maps for this information in a way that's compatible with the unitary. Like that's some task that you need to do as a user of the framework to set up a consistent framework in terms of these maps. Okay, but generally, like coming back to this definition of representation, the important part of it all is that it works for general space-time regions, not just for like single quantum systems or something, but it can take a whole space-time region, and this kind of definition allows you to find a representation on the right-hand side that contains all the information in this space-time region. And on the right-hand side, if I have a subsystem of the Hilbert space, I can assign a quantum state to it. So this way of connecting these representations with space-time regions allows you to assign a quantum system to a space-time region in a way that this quantum state just contains the information that you're interested in. And this is what allows us to define randomness. So for this definition, like in the panorama space, there will be representations for E and for R. And since these are now just subsystems in the Hilbert space, I can assign a quantum state to these regions, which I couldn't on the left-hand side with the space-time. And then we say that our system R is random if it's independent of E, and that means there exist these representations, R arrow and E arrow, such that the quantum state in this panorama space, it factorizes. So this property that I wanted to have before, I can now formulate it, but within the panorama space. And also the quantum state of the randomness, it should be maximally mixed to represent like the uniform randomness. Okay, so in the end, the definition looks like exactly as like, it seems very simple because the framework gives you all the mathematical tools to phrase it in exactly the way you expect it. Okay. Importantly, the framework, like, we don't just have this definition, but you can also show that a simple protocol fulfills this definition. So, I mean, you can come up with all sorts of definitions and frameworks, But this is like, you can show that it's actually consistent with what we expect and it's useful. So this very simple protocol where you just need a C0 gate, it produces randomness in a way according to the definition. So you can see that like it produces the correct quantum state. It's a C0 gate where you have the control qubit in a superposition and the target qubit in a 0 state, which means your state after the C0 gate is this maximally entangled state. And if I now trace out the system R prime, I get this maximally mixed state, which represents my uniform randomness. So this shows that this simple protocol creates the correct quantum state, but you can also, within this framework, show that the other property is fulfilled, that there exist representations such that the state is in a product state like this. I won't show that proof here because it needs a lot of the mathematical details of the framework, but it's important that you have an example where all these things are fulfilled, so it's actually practically useful. Okay, so to give you an outlook of like what else you can do with this framework, you can come back to the device-independent QKD problem about the reusability of devices. We haven't investigated that yet in detail, but the basic idea would be that you put your protocols in spacetime and try to find representations on the abstract Hilbert space that actually capture what's happening there, including that you reuse the devices. And then you have to find some conditions on this state in the abstract space that correctly capture the security of your composed protocols. Another protocol which we're investigating is quantum position verification, where the position of a person is a cryptographic credential. So there's a prover here in spacetime, and he has to prove he is exactly at this point in spacetime. And you can see it's very natural that you need a framework that includes spacetime to be able to show the security of this in a rigorous composable way. So this is also something that we're trying to put like in this framework and get a rigorous security proof for this kind of protocol. Okay, and with this, I'm at the end of my talk, and I'm happy to answer any questions.